even more Laplace transforms. Okay, where are we at? We've still got our definition of a Laplace transform. Integrate from 0 to infinity. Let's get rid of this f of s. We know that it makes a function of, we know that it makes a function of s in the Laplace world. When I take the Laplace transform of a function, I integrate from 0 to infinity, e to the minus st times that function. We have built, using this definition or various other tricks and things, we've built our Laplace transform chart so far. The last thing I think we did in the last video was transforming some of these trig, the sine and cos. So let's just use these in an example to start. Again, the bigger our chart is, the more rules we know, the less integration we have to do. In this example, I don't think we have to do any integration. If I'm transforming this 12 plus e to the t to the 12 plus 8 times t to the 5 plus 7 e to the 2t plus cos 2t, I know that the Laplace of a sum of functions is just the sum of their transforms. So I can transform the 12, that's a constant. So I can transform the 12, that'll be just that constant over s. Plus, I can transform the 8 t to the 5. The 8 is just a constant, so it can come to the outside. The transform of t to the 5, I'm going to use this rule here. Where n is equal to 5. Plus 7's a constant. I need to transform e to the at, where the a is a 2. So I'm using this rule, where the a is a 2. And probably I would just end up putting that 7 on the top. And finally, the transform of cos 2t. So here's our cos transform formula, where b is 2. So this b squared is a 4. So there's a b on top of the sine, and there's no b on top of the cosine. So there, we've transformed this function using the chart. Next example. The next example. The next example is a rule. What happens when I transform a function and it's e to the at times that function? Well, let's pop this in the definition then. Take my definition and see what we get here. So I'm transforming e to the at times that function. Now, common basis of the e, so I'm going to add the exponents. Let's clean that up. When I add the exponents, that's going to be minus s. And now this is starting to look like, well, it's almost starting to look like a Laplace transform of the function, except I wish this s minus a was just s. So I'm going to do a substitution. I'm going to do a substitution where I let that s minus a, I'm going to let that equal to big S. So there's no differentiating, because there's no differentiating my substitution, because I'm just changing this s minus a bracket to capital S. Now when I look at this, oh, this looks like the Laplace transform of f of t, which would be f of, but it's capital S in this case. Oh, and what's capital F? Capital F is s minus a. So the Laplace transform then, the Laplace transform of e to the at times a function is the normal capital F that we would get, but shifted. Let's do this. Let's do an example then. Let's transform this e to the 3t times cos 2t. Now, if f was equal to cos 3t, then big F would be equal to, I'm using my rule up here, the big F would be s over s squared plus b squared. So this would be plus 9. So if little f of t was cos 3t, then big F of s, this is big F of s, would be s over s squared plus 9. But because I've got the e to the 3t multiplied by it, I want that big F at s minus a. So I know what big F is. Big F is this. But everywhere there's an s, I need to put an s minus 3. So it's the shifted function. So it's s minus 3 squared. So now this is the transform of e to the at cos 2t. It's the shifted transformed function. Of course, I might not see it like this. Someone might have expanded this s minus 3 out. So maybe they squared this bracket out. Maybe they wrote this as, if I square that bracket out, that's going to be s squared minus 6s plus 9, if they squared that bracket out, and then they would go plus 9, they just turn that into plus 18. So maybe someone would have simplified, or I would argue not simplified, but just expanded out, changed. Maybe someone would have written it out like this, s squared minus 6s plus 18. How would I go backwards? I would have to complete the square on the bottom, complete the square in the denominator, get back to this stage, and then recognize, oh, that looks like this s over s squared plus 9, except everywhere there's an s minus 3, so it must be the shifted function, so someone must have transformed the e to the 3t times the cos 3t. Oh, think about when we were doing, when we were getting eigenvalues, when we were getting roots of the characteristic equation. If I got eigenvalues of 3 plus or minus 2i, then this would be a portion of the solution. So this is the piece of Laplace transform algebra that would result in a question that has eigenvalues of 3 plus or minus 2i. All right. We'll see more about this when we start to take inverse transforms, when we start to solve whole questions. Now, take the transform of the split function. Here's what we don't do. We have the transform of t. That'll be 1 over s squared. The transform of 0 should just be 0. The transform of e to the 7t would just be 1 over s minus 7. I don't just transform each one of these separate pieces using the functions from the chart, because these chart formula were developed by integrating the same function, the same f of t, from 0 to infinity. But we're not, the function doesn't stay the same. It's t, then it's 0, then it's e to the 7t. It switches. So if I'm going to go do this, I have to go all the way back to the definition, and I'm integrating different functions over different times. So from 0 to 2, the function is just t. From 2 to 4, the function is 0. From 4 to infinity, the function is e to the 7t. So if I'm transforming a split function, I can't rely on the chart rules. I have to go all the way back and go back to first principles and do these three integrations. Well, the middle integration is easy. The middle integration, I'm just integrating 0. The middle integration is 0. But the those other pieces, I need to just work those out. So I do integration by parts on the first piece. So I did integration by parts on the first piece, sub in the top minus sub in the bottom for the f times g. Integrate the e to the minus st over s. The minus signs cancel out. Still integrating from 0 to 2. I've got a sub in the top minus sub in the bottom. I've integrated this 4 to infinity. I still have to sub in the infinity minus sub in the 4. So let's clean this up. Okay, sub in the top, sub in the bottom. When I sub in infinity, I get 0. And here's what I get then. Messy. We're going to learn later, when we learn the Heaviside step function, we're going to learn an easier way to take the transform of a split function. But right now, you have to just integrate e to the minus st over their respective domains for each possible, or each piece of the split function. So it's messy. So we do already have the Laplace of the first derivative, the Laplace of y prime. What about the Laplace of the second derivative? Well, the way we'll set that up is, let's think of the second derivative as the derivative of the first derivative. So it's y prime prime. That way, I can use my Laplace formula for the derivative where this is. So it's going to be s times the Laplace of, well, in this case it would be the Laplace of y prime minus y prime naught. And all I need to do now is, what's the Laplace of y prime? I can directly use the formula from my chart in here. So that would be s times s, the Laplace of y, minus y naught, minus the y prime naught. So let's clean this up. That'll give me the Laplace of y prime prime is equal to s squared times the Laplace of y minus s y naught minus y prime naught. And y naught, that's the initial condition. That's a number. That's given in the question. Y prime naught, that's an initial condition. That's given in the question. Those are both numbers. So let's add this to our chart. And we'll put it in right here. So now I can take the Laplace of the first derivative, the Laplace of the second derivative. I guess I can take the Laplace of the third derivative as well, but let's jump right down to where we'll take the Laplace of the nth derivative and see if we can see a pattern here. So I'm thinking of then taking the Laplace, if I wanted the Laplace of the nth derivative, I'm thinking of that as the Laplace of the n minus 1 derivative primed. So I'm setting it up in the same fashion as we did the second derivative, because that would just be s times the Laplace of the unprimed piece. So just the n minus 1 derivative minus the nth minus 1 derivative naught. So that's a number. And then all I need is the nth minus 1 derivative. We know what we're going to do. It's going to be the same setup as this. Be a proof by induction. we'll end up with, I'm going to go ... If we do a proof by induction with this, we'll end up getting the Laplace of the nth derivative of a function is equal to s to the n times the Laplace of that minus s to the n minus 1 times y naught minus s to the n minus 2 times y prime prime naught minus, okay, ... Notice the power of the s goes down 1 each time, and the number of the derivative goes up 1 each time, until finally you end at the nth minus 1 derivative evaluated at 0. So the one before, the one right before that, let's put the one right before that. The one right before that would have, it would be the n minus 2 derivative, and there would just be one s here. The power of the s, 1, plus the number of the derivative always equals to n minus 1. So there's our general formula for the Laplace of the nth derivative. Most likely in our exercises, we're going to do taking the derivative or the Laplace transform of the first derivative, the second derivative, maybe the third derivative. But with this formula, we can take the derivative of, or we can take the Laplace transform of any derivative. So here's a problem. I look at this linear second order constant coefficient non-homogeneous differential equation. If I were to solve it by getting the eigenvalues, getting the particular solution, and adding it to the homogeneous solution, I would see that the homogeneous solution, the eigenvalues would be 2 and 3. So this portion would be the homogeneous solution. The particular solution would be a line, because I'm trying to hit a line, so I would figure out what the particular solution here, A would be some number, B would be some number. I would probably use unknown coefficients to figure out the numbers for A and B. So this is the form of the solution that I expect. Let's solve this with Laplace transforms. Step 1 then is Laplace both sides of this equation. Taking the Laplace of y prime prime, second derivative. So that'll be s squared times y minus s times y naught minus y prime naught minus 5 times, now I need the Laplace of y prime, which would be sy minus y naught, and then plus 6 times the Laplace of y equals the Laplace of t. The Laplace of t, using our formulas, 1 over s squared. So now our next step is going to be solve for y. When I solve for y, well, there's going to be y times, what do we got here? You got an s squared times the y, a minus 5s plus 6. There's the auxiliary equation. Those are all the pieces with a y on it. The only piece that doesn't have a y on it is this minus 1, and when it goes over to the other side, it's a plus 1. So I can see the auxiliary equation there. Let's simplify this together here. So I simplify that together so that when I solve for y, I'm getting y equals this piece, and I'm dividing this bracket out, but as I divide it out, let's factor it. So there's s minus 2 times the s minus 3. Now I need to break this up into partial fractions. So I broke this up into partial fractions, Now I can unlaplace each piece, unlaplace each side. So capital Y of S unlaplaces to be little y of t. Here I've got a number, 10/9 times e to the 3t. I expected to get a number e to the 3t plus minus a number e to the 2t plus a number, a constant would have Laplaced to a constant over s, so this unlaplaces to be the constant, plus 1/6 times t. So if you were to plug in t equal to 0, you'll see that that gives me out 0, so it does go through the origin. If you were to differentiate this, then plug in 0, it'll have a slope of 1. It'll go through the point 0, 0 with the slope of 1. So our initial conditions are matched, and it is the form that we expected. A line for the particular solution, and a linear combination of e to the 2t and e to the 3t because of the eigenvalues or roots of the characteristic equation of 2 and 3.